Um, Good morning. Morning. In today's lesson, we will be focusing on electromagnetism, right? So today we'll be dealing with how electricity is able to be generated from a magnet. Yes, we'll be focusing on how magnets are responsible in the formation of electricity. Let's look at the notes that I've given you. These are the notes. So, in this session, we'll be focusing on number one, the right hand rule. Right? Then, secondly, we'll be looking at the factors affecting or influencing the magnitude of an induced EMF. Thirdly, or lastly, we'll be focusing on Faraday's law. Right? Now let's move. This is our magnet. So if you are being asked anything about the magnetic field lines, you must know that the magnetic field lines always move from what? A north pole going to a south pole. If you look at the direction of the magnetic field lines over here, they are moving from a north pole of a bar magnet to a what? South pole of a bar magnet. And another thing that you must pay attention to is that the lines do not cross each other. And the wider the distance between them is the weaker the force, electromagnetic force, and the more closer they are, it illustrates a what? A greater force. Let's continue. Right hand rule. Now, the right hand rule simply states that the thumb will point in the direction of the current, and the curling fingers. Let's look at picture number one. The thumb, this is the thumb that I was talking about, is pointing in the direction of what? Of the current flow. Whereas these are the curling fingers. These are the curling fingers. Now these curling fingers will point in the direction of the magnetic field. Right? So, if we introduce a bar magnet, let's look at picture number 2 over here. Sorry. If we look at the magnet over here, the law does not continue as it says. It now says that the thumb will no longer point in the direction of the current, but it will point in the direction of the north pole. So here's the thumb pointing in the direction of what? The north pole. Whereas the curling fingers now, this finger over here, will be pointing in the direction of what? in the direction of the current. That is your right hand rule. The thumb can either point in the direction of the current. The curling fingers can either point in the direction of the magnetic field. Also, the thumb can also point in the direction of the North Pole, whereas the curling fingers, these fingers that are curling over here, will be pointing in the direction of the current. Are we fine? Let's continue. Now, we are looking at the factors which affect the magnitude of the induced EMF. Now, before we go there, we are going to look at a warning or a principle. Yes, let me call it a principle, the right hand principle. Here I've written ND, notabile. Now, the direction of the reading on the galvanometer will point in the direction of the current. Don't worry, I'll explain it to you. And let's look at the factors which influence the magnitude of the induced EMF. Number one, the strength of the magnetic field. Right. So, if the magnetic field of your magnet is weak, I have explained that if the magnetic field lines are far apart, it illustrates a weak magnetic field. Whereas if the magnetic field lines are closely packed, it illustrates what? A stronger magnetic field. So, let's look here. We are saying that the strength, how strong or weak the magnet is, the strength of the magnetic field can be a factor which influences the magnitude or the size of the induced current. Right? The stronger the magnet, if the magnet is strong, the greater the induced current. What does this mean? If we have a magnet which shows stronger magnetic field lines, it simply means it's a stronger magnet. So the greater or the stronger the magnet, the greater the induced EMF or current. Number two, we're looking at the number of turns within a coil. The number of what? of turns within a coil. We know what a turn is. We use a different color, use a favorite color. So the number of turns within a coil will illustrate or will affect the magnitude of that induced current. Meaning that the greater the number of turns, the greater the induced EMF. Lastly, the speed at which the magnet and the coil are removed relative to each other. So if the higher or the greater the speed, the greater the induced EMF. The faster we put our magnet in a coil, the greater the induced EMF. We must be able to understand and be able to apply the knowledge that we have. So we have three factors which affect the induced EMF or the induced current. Number one, we are looking at the strength of the magnetic field. The stronger the magnet, the stronger the magnetic field. Secondly, we'll be looking at the number of turns in a coil, the number of turns in a coil. So the greater the number of turns, the greater the induced current or EMF. Thirdly, or the last, we are going to look at the speed at which the coil and the magnet are moving relative to each other. So the faster we put or we throw or we push our magnet bar inside a coil, the greater the induced EMF. Now let me pause here.